Project-based learning, DNA information storage. In algebra, I learned how to convert the letters of my name into DNA and found out how long it would be if it were written in actual DNA. I can't draw DNA very well. First, I assigned every letter of the alphabet with a number, A1, B2, C3, etc. These are the numbers that represent the letters of my name. I converted each number into base 10 using this chart. Using the number 1234, you can see that the 1 lines up with the 1000th place, which is represented by 10 to the third, and so on with the rest of the numbers, ending with the 4 in the ones place. While doing this project, I learned about the general rule of exponents. For example, if you had 10 to the third times 10 to the second, you add the exponents, 3 and 2, and end up with 10 to the fifth. So the general rule is a to the x times a to the y equals a to the x plus y. Next, I converted my base 10 numbers into base 4. I did this because there are 4 bases in DNA: adenine, thymine, cytosine, and guanine. I drew a chart similar to the base 10 conversion chart, but instead of the base being 10, it was 4. I also learned that you could use the distributive property to make multiplying easier, so if you had 4 times 16, you could break 16 down to 10 and 6. You'd multiply 4 by 10 to get 40, then 4 by 6 to get 24. Then if you needed to, you could break 24 down to 20 and 4, then add 40, 20, and 4 to get your product of 64. To actually convert the numbers, let's use m, which is 13, for example. I had to find the biggest number that went into 13 on the chart, which was 4, and write how many times that number went into 13, which was 3, with 1 left over. So in base 4, these are the numbers that represent the letters of my name. My name doesn't give a letter in base 4 that's bigger than 2 digits, but the letter X from my last name would be 121 in base 4, so I wrote all the letters of my first name with 3 digits instead of 2. While working on this project, I learned about Rosalind Franklin. She was largely involved in the discovery of information about DNA with Watson and Crick. Although Rosalind made the discovery, Watson and Crick were given the credit for it, and were even awarded with Nobel Prizes. Rosalind was not, because she was a woman. Next, I assigned each base 4 number with adenine, thymine, cytosine, or guanine. I did this by assigning A, T, C, and G with numbers. A was 0, T 1, C2, G3. After I wrote out my name in DNA code, I made a model of it. I decided to use paper clips. Adenine was represented by yellow, thymine was blue, guanine was pink, and cytosine was red. The white paper clips represent the connectors. I know that A matches with T and C matches with G. A way to remember this is that A and T consist of straight lines, but G and C have curves. This is the model I made out of paper clips. Next, I measured the chain of paper clips and saw that it was 20.5 inches. This made me wonder, how long would it be if it were actual DNA? What's the scale of my model? I decided to look it up. I started at Wikipedia, then went from there, making sure the sources I found were reliable. I found an article by a professor of biochemistry at the University of Toronto and decided that was a good source. I learned about BPs, or base pairs. One base pair is 0.33 nanometers. Not knowing what nanometers were, I went farther into my research. I learned that a nanometer is 1/billionth of a meter. In scientific notation, a nanometer would be represented by 1 times 10 to the negative 9th meters. I had 18 base pairs, so I did 18 times 0.33 times 10 to the negative 9, and got 5.4 times 10 to the negative 9, which is 594 100 billionths of a meter. But this is meters, and my model was inches, so I learned to convert inches to meters. I found out that 1 meter equals 39.3701 inches. I cross-multiplied 1 meter times 20.5 inches and x meters times 39.3701 inches, and got 39.3701x equals 20.5. I divided by 39.3701 on both sides, and came to the conclusion that x equals 0.520699719 meters. To find the scale of my model, I cross-multiplied again. I multiplied 0.5206997 0.7188 meters by x and 1 meter by 5.94 times 10 to the negative ninth. With 5.94 times 10 to the negative ninth equal to 0.5206997,188x, I divided each side by 0.5206997,188 and came to the conclusion that 1 meter on the model is equal to 1.1 times 10 to the negative 8 meters in actual DNA. I'm Amelia, and this is the end of my math video.